course, when we got our prototype circuit back, we could debug it by poking around our system board with all kinds of nifty probes. We had test equipment, scopes, and logic analyzers and stuff that helped us find those last few problems in our design. But with modern FPGAs, we have systems on chip. Very cool. My system is now on a chip. Very uncool. How the heck am I supposed to poke around with my probes and find my bugs? Huh? Luckily, the clever folks who make these chips thought of that problem as well, and have given us something called in-system debug that lets us put virtual probes and instruments into our circuit of virtual components, so we can debug virtually anything. Hi, I'm Amelia Dalton, host of Chalk Talk. Today my guest is Ron Plyler of Xilinx, and we're going to chat about the in-system debug capabilities of Xilinx's all-programmable devices using Vivado. Before we get started, remember to click that link. There you can check out a tech packet where you can download a free Vivado Design Suite user guide and tutorial called Programming and Debugging. Welcome, Ron. Thanks so much for joining me today.
Thanks, Amelia. Thanks for having me.
So, Ron, when I finish an FPGA design and load up a bitstream into my dev board, it always works perfectly the first time. But I understand that for some people, that might not be the case. There's this thing called debug. Okay, not really, but...
Yeah, that's true. Some people do have to actually debug their designs.
Yeah.
Well, with today's designs being larger and more complex, it places even more burden on verification and particularly debugging the hardware. With all the complicated interactions between different subsystems in the design, imagine how nice it would be if we had an on-chip logic analyzer to work with. It could be built out of spare logic resources and block RAMs for storage, and would probe and capture internal signals during real-time hardware operation, and the captured data could be analyzed in a graphical waveform viewer. Wouldn't that be great?
That would be great.
Well, as a matter of fact, all this and much more is already made possible with the Vivado Design Suite in-system debug.
Sounds awesome. So what's the philosophy behind in-system debug? Do we just wait until we get into the lab and find out that we have problems and start connecting probes? How do you connect up a probe to a LUT anyhow? No matter how I try, Ron, it just doesn't.
Well, like many of our core Vivado features, debug is paired with a proper methodology.
Sure.
And we recommend planning the hardware debug early in the design cycle. Consider upfront what internal signals are going to be worth probing.
Sure.
Keep in mind, just like designing, debugging is also an iterative process. Attach some probes to internal signals and implement the design. Then download the design and analyze the probes during hardware operation. This enables us to observe and find bugs and fix them. And finally, we get to a state where the hardware is operating properly and no more bugs are found. Because FPGAs are reconfigurable, debug is naturally an iterative process that aligns with the iterative design process.
Sure. So out of curiosity, what actually goes into a design for debugging?
In Vivado, the debug logic consists of IP cores as the building blocks.
Okay.
It's a natural fit for the functions that cover the basic debugging tasks like monitoring internal signals and injecting logic values, all while the device is running in real time. First we have the ILA, or Integrated Logic Analyzer. The ILA is connected to the internal signals to be probed. Those signals can be captured according to a conditional trigger based on hardware events and captured at system speed. The ILA can store entire data windows for analysis, so it works very much like a logic analyzer built into the design.
Oh, okay.
The Virtual Input-Output VIO debug feature can both monitor and drive internal FPGA signals in real time. It's a little different than the ILA. It doesn't have the storage capacity, so it's not intended to capture a window of samples. It's really more for static control signals, things like reading and writing control signal registers.
Okay.
And the JTAG to AXI master generates AXI transactions that interact with AXI slaves, both AXI full and AXI light. These transactions are reads and writes into a system that is running in hardware in real time. This is a convenient way to directly access any type of AXI slave without having to go modify embedded code. So this core can be used in designs without processors as well.
I see. We put these debug IP cores in the design and connect them up to internal signals for probing. Now, how do we actually go about doing that?
Right. It's important to understand the design flows behind the debug methodology. There are a couple of flows Vivado supports. One is called the Netlist Insertion Flow, and the other is the HDL Instantiation Flow. Let's take a look at the Netlist Insertion Flow first. What do we mean by that Netlist insertion?
Yeah.
In general, we don't have to modify the HDL source files to add debug logic. Instead, we just choose the signals we might want to probe, and what we mean specifically are nets, net objects in the design as opposed to pins and ports and cells, which are not probed.
Okay.
There are a couple of ways to choose probes. We can add a mark debug attribute on nets in HDL, so we do need to touch the HDL, but we don't really change anything as far as the functionality.
Ah, okay.
See, in this example, we put mark debug true on these two wires, which tells Vivado that we are interested in these as candidates for probing.
Okay.
Alternately, we can work on the synthesized netlist and choose nets that way. Select a net and apply an XDC constraint for mark debug. That all goes to an XDC file, so we don't have to touch any design sources.
Ah, so we tag some nets as potential probing candidates. What comes next?
Once we have the candidate probes identified, Vivado will take care of connecting them.
Ah, okay.
We call the debug setup wizard. This is where we actually choose which nets out of the candidates that we actually want to hook up probes to.
Okay.
The wizard steps us through this process, and when finished, Vivado automatically inserts all the necessary debug logic into the netlist and connects up the probes. So that should explain the name Netlist Insertion Flow.
Okay, that sounds pretty easy to use, relatively non-invasive as far as my design, but what about the other flow?
That would be the HDL Instantiation Flow. As its name implies, the debug IP is instantiated in the design. First, we generate the debug logic as an IP core. This can be done by going to the Vivado IP catalog where we choose the type of debug core we want to generate. Just as we would do with any other type of IP core, for example, we chose the VIO here, which is only supported through HDL instantiation.
Okay.
We go through the customization and generate the IP.
Then we can just instantiate this into my design?
Yes, and manually hook up the core to our internal signals that we want to drive out or monitor. Just basic HDL instantiation, which has been around for thousands of years.
Yes, I heard that's how the dinosaurs went extinct. They stayed with schematics.
There is a much more modern way to do this.
Excellent.
Many Vivado users are quickly adopting IP Integrator for design and adding debug logic to their block designs. Let's take a look at how that works. Here's our block design where we want to add an IP, so we just right-click.
Okay.
And in this case, we're adding a JTAG to AXI master. Remember, the JTAG to AXI master actually drives out complete AXI read and write transactions. We can create transactions in real time using tickle commands, which is pretty nifty. After configuring the IP, the symbol gets plopped down on the diagram. Notice the green bar here that says Designer Assistance Available. It contains a link to run connection automation, so we choose to run automation, and we end up with our JTAG to AXI master automatically integrated into the block design. When we run through the flow, the block is instantiated in the generated HDL.
Okay, we've covered quite a bit here, Ron. Can we back up and summarize just a tad?
Sure. To summarize the different debug flows, first, the Netlist Insertion Flow, which has very little impact as far as source code modifications, and allows us to maintain our probes and set up separately if we want to.
Okay.
We can tag nets for debugging at various design stages. About the only drawback is that when we tag a net for debugging, it doesn't actually get hooked up to a probe until we say so there is a chance it could get optimized away.
Ah, okay.
Then the HDL Instantiation Flow. Why would we want to use this flow? Well, if we have a good idea up front of what we plan to debug, then this lets us implement exactly what we want, and we don't have to worry so much about managing it afterwards.
Oh, okay.
We can use this flow with HDL and IP Integrator. The drawback is that when we want to change probes, then we need to modify the connections in the design sources.
Ah, okay.
It is possible, and it may make sense to use both flows in the same design. And both flows are compatible with projects and non-project mode in Vivado.
Oh, okay. So I think I understand how to get debug logic in my design. How do I actually debug my design?
Well, once we have the necessary cable hookups to our hardware, everything can be managed using the Hardware Manager.
Okay.
In the Vivado IDE, this is launched from the bottom of the Flow Navigator. The Hardware Manager allows us to connect to hardware containing one or more FPGA devices to program and interact with those FPGA devices. When we are ready to debug, the steps to connect to hardware and program the target FPGA device are: open the Hardware Manager,
Okay.
open a hardware target that is managed by a hardware server running on a host computer, and it's possible to connect through Vivado over the network to that host computer so we can actually debug from remote locations. We don't have to actually be in the lab.
Cool, okay.
Associate the bitstream data programming file with the appropriate FPGA device. Program or download the programming file into the hardware device.
Okay.
Then, when the hardware is up and running, the hardware manager becomes a control center for all debug activity. We can see the status of everything, including the hardware being monitored, the probes and their triggers, and properties of the debug cores themselves. There are also dashboards for the debug cores, so we can quickly visualize what's happening. For example, this VIO dashboard has color-coded status of the signals being probed and push buttons for applying logic values.
Okay.
After some data has been captured from our probes, we can analyze the data in a graphical waveform viewer, which makes analysis just like analyzing a logic simulation run with markers and other features.
Okay, I think I'm following along pretty well here. What if I want my black belt?
Okay, yeah, now for some of the advanced stuff.
All right.
We can configure certain options to control how much data to capture and when to capture it. We can create simple Boolean trigger patterns built with signals that we're monitoring that start the data capture.
Okay.
This allows us to only capture the data at the conditions where it matters to us. This ensures a most efficient storage of captured data in the on-chip block RAMs. There's a new feature we call Advanced Trigger Capability. When we set up our ILA, we can specify advanced triggering, and instead of triggering on simple Boolean expressions, we can get access to triggers based on complex state machines, described in a simple, intuitive state machine language.
Okay.
We can search for patterns sequentially and also perform conditional capture. There are also programmable counters and flags, and all this can be done in real time while the hardware is running. Everything we mentioned so far is inserting debug logic cores and setting up probes and connecting them. This can all be captured as a set of XDC constraints.
Okay.
This is actually pretty powerful. If we're using the Netlist insertion flow, then the entire debug setup can be managed separately from the design sources. It can be stored in an XDC constraints file.
Okay, Ron, I think I followed along pretty well, even with those black belt features, but I think I need a bit of a recap.
Okay, overall, Vivado has a very capable and comprehensive debug solution. A powerful, capable set of IP cores for the debug logic, the integrated logic analyzer, virtual input-output, and the new JTAG to AXI master, flexible design flows, Netlist insertion, which allows debug needs to be managed separately from the design, and HDL instantiation, which allows complete control over debug setup and supports IP integrator block designs. The hardware manager, which lets us program our devices and then begin debugging in real time, keeping all debug activity well organized in Vivado in one place.
Cool, okay.
And lastly, all features are XDC and Tickle compatible for projects and scripting in Vivado.
Excellent. Well, I think I'm ready to get started, I think. Where can I go for more information?
Well, remember there's always more to see at www.xilinx.com. There are Vivado quick take videos on programming and debug, as well as a user guide UG908 and a tutorial UG936, and finally the Xilinx user community forums where you can browse topics of interest, share ideas with other Vivado users, and get help from Vivado experts.
Sounds great. Well, I think that's all I have time for. Thank you so much for joining me today, Ron.
Thanks, Amelia, for having me today.
Before we go, remember to click that link. There you can check out a tech packet where you can download a Vivado Design Suite user guide and tutorial called Programming and Debugging. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.